All right, good afternoon. Welcome back. So how's everyone doing?
Good, Nick. How are you doing?
Pretty good, thanks. All right, well, first thing I want to go over is the homework 3 that I graded and posted comments on. Let me go through that, and then we can go through questions that you have on homework 4, the current homework. And then once we're done with that, we'll go back to talking about number theory. All right, so let's do some homework 3 comments. So pretty much everybody has the right idea for doing these proofs, which is awesome because most of what we're going to do in this course, well, the majority of what we're going to do in this course comes down to being able to do proofs in one form or another. Sometimes they're very formal with all the funny symbols and things like that. Sometimes they're more kind of conversational, but the underlying strategy is always the same, which is we write a series of propositions, and each thing that we write has to be a true statement based on either things we know or some combination of the things we've already shown to be true, which could be hypotheses, could be a negated conclusion that we're assuming, or could be things that followed from previous statements, and we work our way through to hopefully a proof of whatever we're trying to show. So so I looked at question 3.42 in detail, and that was a question we actually worked through on Monday, which was showing that the following is a fallacy. If P, then Q, and not P, all taken together implies not Q. And we worked through this with a truth table. Truth tables are a really good way to show if something is true or not by simply looking at all the possible values of P and Q. To show something is a fallacy, it's sufficient to find a counterexample. As long as it's a carefully chosen counterexample where absolutely we can pick propositions P and Q, where P implies Q and not P, and therefore not Q. So let me see. Let P be the proposition x equals 5. Let Q be the proposition x is bigger than 0. Okay, P implies Q is true. If x equals 5, then x is bigger than 0. Okay, suppose x is equal to 6. All right, well, if P then Q is still true, right? If x is 5, x is bigger than 0, that's absolutely a true statement. So P implies Q is true. Not P is also true. P is the proposition x equals 5, while x is 6, so not P is also true. So P implies Q and not P is true. However, not Q is false. Q says x is bigger than 0, not Q says x is less than or equal to 0, and that's false because x is 6. So this is suggesting that this left side, which is true, implies a right side, which is false. And that's not an implication, right? If this statement was true, if that was a true proposition, then any time that this is true, this would also have to be true. And here we have an example where that left side is true, but the right side is false. So that would be a valid counterexample. But you can also do this with a truth table. And I believe we did that on Monday. The the one comment I made in some people's submissions to this, though, is that they tried to show that this was not equivalent to this. They came up with a value for this and a value for this, and they were different. This is not the same as equivalence. Okay, saying that you know, x implies y is different from x is equivalent to y. Equivalence is a much stronger statement, because x could be false and y could be true, and this implication is still true. But for x and y to be equivalent, if x is false, y would have to be false also. And so if we look at the truth table, and it makes no difference if I'm doing a single arrow or a double arrow. The double arrow is just a way to avoid writing parentheses, because it says everything on the left gets taken together and implies everything on the right. But if we do a truth table, the implication is always true except in the case where the hypothesis is true and the conclusion is false. Any other time it's going to be true. But equivalence means that these things have to have exactly the same value. And so in this case, equivalence and implication differ. And in some way it's easier to imply than it is to be equivalent. So that was the only sort of general comment on 3.42. And if you're doing this, you know, on a test or in a court of law or something, right, you want to go beyond simply showing this in your truth table and showing that in your truth table. Show the value of this implication also, and show clearly that there's a case where this is false, right? In particular where this is true and that is false. And that sort of takes us to the business of proof. So the other things I looked at were the 6 questions in 3.5.4. So A, B, and C, direct and indirect proofs. And I looked at those in detail. Someone said if they're doing this in court, they're in big trouble. There's a story, it's probably urban myth, of a mathematician who went to court and claimed that he could prove that God existed. This was a long time ago. Claimed that he could prove God existed, and he basically wrote down some mathematics, and the people judging the case had no idea what he was writing, and they said, well, I guess you're right, because they didn't want to sound like they didn't know what he was talking about. And so he proved God existed that way. So yeah, maybe not bad if you're in court. All right, so these proofs. So as I said, looked like people had the right idea in going through step by step. Couple of specific things to keep in mind. First of all, indirect proofs are a very specific thing. So let's take a look at this 3.4 or 3.5.4. Let's just look at question A. And we were asked to show the following. Given if P, then Q, if not R, then not Q, and not R, we can conclude not P. Alright, so direct proof. And I think we already did this one before, but let's go through it again anyway. So I'm going to do this in a different order. I'm going to do this in the order in which I kind of think of it, which is I see a not R and I see not R implies something. So I'm going to go with those first. So I'm going to write down not R. And that's a hypothesis. I'm going to write down not R implies not Q. And that's a hypothesis. And then I'm going to put those together. And since I have not R and not R implies not Q, I'm going to conclude not Q. and that's direct reasoning 1 and 2. And then I'm going to write down if P then Q, that's a hypothesis. And now I can combine 3 and 4 using indirect reasoning, and I can conclude not P, and that's indirect reasoning 3 and 4, and that's what we were asked to show. All right. So, so the QED comes after you've shown the thing that you were asked to show. I can't write QED at this point, unless I was asked to prove if P then Q. And to us who understand this stuff, right, it's pretty clear at this point, if we know indirect reasoning, that these two go together, they'll get us not P. But we have not shown that in our proof. You have to actually state that, right? Now I have proven not P is true because of indirect reasoning applied to steps 3 and 4. And once I've written this down, since that's the thing I was asked to prove, now I can say QED and my proof is done. Okay, let me show you an indirect proof that's not really an indirect proof. So an indirect proof, remember what we do is we negate the hypothesis and we argue to a contradiction. Well, I could throw some step in here which says P. Let me write that clear. I could throw some step in here which says P, and that's the negation of the conclusion, right? And I can go through my direct proof and prove not P, and now I can say P and not P, and that's from steps 1.5 and 5, and that's a contradiction. But I think you can see this is really just a direct proof, right? It's a direct proof of not P, and now I'm saying, and if I negate that conclusion, it contradicts the fact that not P is true. So not P must be true. Yeah, technically that's true, but really once you've proven not P, you're done with a direct proof of that. Okay? So let me show you what an indirect proof would look like. And think about the difference between these. An indirect proof, we start off with, we might have some of these things here, like, if P then Q, that's a hypothesis. But we negate the conclusion, and we use that as part of our proof. We don't just kind of leave it here so that after we've directly proven the conclusion, we say that's different from the negation of the conclusion. That would be a contradiction. Right? So we take the negation P in this case and we somehow use that as part of a direct proof of a contradiction. So in this case, P implies Q. P, that would give me Q by direct reasoning using steps 1 and 2. And then not R implies not Q. That's a hypothesis. And so indirect reasoning would give us R using steps 3 and 4. And now we can bring in our hypothesis, not R. That's a hypothesis. And that's a contradiction between steps 5 and 6. So I didn't take off points if you did this, but I put a comment in the notes on Canvas saying, this looks like a direct proof rather than an indirect proof. So think about the difference between this and that, right? And maybe go back on your own and try to redo those indirect proofs. Make sure you know how to do that, because you'll see some of these on the midterm, okay? And on the midterm, I'll want to see an actual indirect proof where you use the negated conclusion to reach a contradiction, other than, I already showed not P, so this is a contradiction. So yeah, comment in chat. So is it safe to say that for an indirect proof we need to use the negated conclusion at some point? Yeah, you need to use it in some way other than just at the very end after you've directly proved the non-negated conclusion. So you need to use it inside the proof. So is any contradiction enough for an indirect proof? Yeah. Basically, if you can prove that false is true, that's your contradiction. So really what's happening here is I've proven R and I've proven not R. Well, since both of these things are true, R and not R is true. And there's some negation theorem, maybe there's some theorem on page 58 which says this is equivalent to false. And now I've proven that false is true. That's the quintessential contradiction. But at this point, if you just want to say 5 and 6 contradict each other, and it's really clear because it's R and not R, right, that's good enough. But if you have to do some thinking to see that 5 and 6 contradict each other, keep going with your proof, right, until it's irrefutable to somebody looking at this without doing much thinking that you have a contradiction. Let's see. Oh, and because false implies true, the whole thing is false. I don't know about that. The problem here is that true is implying false, right? All of these things that are true ends up implying false, and that's not valid, right? True can never imply false. So I don't understand why indirect proofs are a thing when you can just use a direct proof. So in these homework questions, it's kind of just an exercise. But yeah, there are cases where an indirect proof will work really well, and a direct proof may not work as easily. I don't know if there's situations where you cannot use a direct proof. There's certainly questions where I don't see how to do it with a direct proof, but I think it's a deeper question of are there cases where it's impossible to do a direct proof? I'm not sure. But let's see. Let me try one off the top of my head. Prove that if a times b is less than n, then a is less than the square root of n, or b is less than the square root of n. Where a, b, and n are all positive. So prove that if the product of two positive numbers is less than n, then at least one of them is smaller than the square root of n. And maybe there's a way to do this with a direct proof, to start off with a times b is less than n, and then take the square root of n over here, and this is the square root of a times the square root of b. But I don't know how to directly show this starting with that. But an indirect proof is really easy. So we want to prove that this or that is true. So step one, I'm going to assume the negation of a is less than square root n, or b is less than square root n. That's the negation of the conclusion. And if I De Morgan that tells me a is bigger than the square root of n, and b is bigger than or equal to the square root of n. That's De Morgan's theorem. And I'm also told AB is less than n. That's a hypothesis, right? That's the hypothesis. And now I can just do some algebra from step 2 and say AB is bigger than or equal to square root n times square root n, which is equal to n. That's algebra and substitution from statement 2. And now I have a contradiction. Because statement 3 says AB is less than n, statement 4 says AB is bigger than or equal to n. And those two statements contradict each other. And therefore, this negation must be false, which means that the non-negated conclusion must be true. So that's like a 5-line proof if you use an indirect approach. Don't know how to do it directly. But even for these homework questions, sometimes some of these questions in indirect proof will feel very sort of easy to get to, and a direct might be kind of convoluted, or vice versa. All right, so things to watch out for, things to avoid in proofs. So again, never write down something in your proof that's not true. If I'm doing a direct proof, I'm starting with things that are true and trying to get to my conclusion. If I write not P somewhere in here, my proof falls apart at that point. Right? The only time I can write not P is when it follows from things that I've already written. For example, indirect reasoning apply to 3 and 4. Now I can write down not P. But don't write it down in the beginning and say, you know, what we're trying to prove or something like that. That invalidates your proof. All right. This is a little subtle, but it's really important. Let's try this proof again. All right. So let's write down step 1. I'm going to do not R. That's a hypothesis. And step 2, I'm going to write not R implies not Q. That's a hypothesis. All right, and this is what we're trying to prove. Okay, don't do this. So step 3, not R and not R implies not Q implies not Q. All right, what's wrong with what I just wrote? Technically, there's nothing wrong with it. It is a true statement. But it is true regardless of steps 1 and 2. What I've done is in the middle of my proof, I've written down the formal statement of direct reasoning. Now, this is a true statement, and I can put any true statement in here that I want. I can put down, if it's sunny out, then I'm going for a run. But this is not the same thing as writing not Q. Okay? This is entirely different from writing not Q. I can use this, and I can combine it with steps 1 and 2, and I can say not Q. And the reason for that is, you know, direct reasoning using steps 1 and 2. But all I'm doing here is I'm writing down a theorem from page 59 of my textbook, something called direct reasoning. So if you're trying to say not Q, write not Q. Okay? This is a proposition, but this proposition does not say not Q. It says, given this and that, we can conclude not Q. But you haven't written not Q yet in your proof yet. And if I'm going to try to do something like indirect reasoning, right? I can take not Q and I can take this statement. I can use indirect reasoning to conclude the negation of not R. That's fine. But if I don't have this, and I try to combine steps 3 and 5, steps 3 and 5 don't go together. To use indirect reasoning with step 5, I need to know that not Q is true, and this does not say not Q is true. This says that if I know this, and I combine this and this using this, then I'll be able to conclude not Q. But you haven't done any of that yet. You gotta actually say not Q. And if I'm going to say not Q and I'm going to list direct reasoning, there's no reason to do this. Just like there's no reason to say, 1 plus 1 equals 2. It's a true statement. It doesn't invalidate my proof, but it doesn't help me either. And you don't really want to put things in your proof that don't help you. All right? So I understand the goal in seeing this, right? And I didn't take off points for this, but I will in the future. But this is not the same thing as writing down what happens when you use this principle on previous statements to conclude, in this case, not Q. Okay? That's a kind of subtle but really, really important point. Okay, and if you gave this proof to somebody and you had this instead of this, they would probably not be able to follow why this led you to that. Right? Because they would say, well, but you haven't proven not Q. Oh yeah, we showed 1 plus 1 equals 5, I forgot. Alright, so that's a detail of sorts. Let's see, anything else I wanted to say on here? I think that was it for things that I saw. And like I say, despite notational things like this, it seemed like most people knew how to do these. They were able to put the things together that they were given and prove the conclusion. And there's a variety of ways to do this, right? Different people had different approaches. Some people don't like working with conditionals. They'll turn these into conditional equivalences and work with the ands and the ors. Some people will take ands and ors and turn them into conditionals. All of that's valid. Some people don't like negation, so they try to use De Morgan to get rid of them. Nothing wrong with that. It's all valid. All right. So any questions either on any questions on homework 3, the stuff we've just been talking about? Any other concerns or questions on that? All right. Questions on homework 4? Let's see. Can I use the contrapositive and prove that? Prove that 1 plus 1 equals 5? Maybe. What's the definition of an even number? An even number is a number that can be written as 2 times an integer. So, definition. N is even if there exists an integer k such that n equals 2 times k. And n is odd if there exists an integer k such that n equals 2 times k plus 1. Probably takes some work to show that every integer is either even or odd. It can be done, but it might take some work. Can I use the contrapositive to prove 4 and 5? This 4 and 5? On our homework for this week, sorry. Gotcha. So question 4, prove that if n squared is even, n is even. Prove that if n squared is odd, then n is odd. Those are questions that I do not know how to prove directly. So I think you are definitely best off using an indirect proof for those. And that means basically using the contrapositive. And let's just spec that out a little bit. Let's look at question 4 on this week's homework. So prove if n squared is even, then n is even. Well, an indirect proof will start by negating the conclusion, right? N is odd. And we'll eventually arrive at a contradiction, which will be n squared is odd. And that contradicts n squared is even. Right? So you do a direct proof that if n is odd, n squared is odd, and that will give you this. But the contrapositive of this statement, right, would be the following. If not n is even, then not n squared is even. Okay? This statement is logically equivalent to that statement, because we know a statement and its contrapositive are equivalent. So the statement, if n squared is even, then n is even, is logically equivalent to the statement, if n is odd, then n squared is odd. So if you prove this, right, which you can do with a direct proof, you can say, since this is true, the contrapositive is also true, which is this statement. That's another way of looking at the fact that if we do this and we conclude this, we've proven the original statement. So a proof by contradiction is really just a direct proof of the contrapositive of your original statement. How do you know that an indirect proof is easier? Are there clues we can look for? Yeah, if you're pulling your hair out trying to do a direct proof, try an indirect one. And that's seriously the only guidance I know. I don't know of anything else that sort of tells you one way versus another is the best bet. But, you know, if you don't even know how to get started, or you try to get started and you just end up with things that look hopeless, then try the other approach. And probably there's some intuition that can be developed over time. I've never developed that. But I don't spend a lot of my life doing proofs. So yeah, just play around with it. And sometimes you go back and forth. You know, you try direct and it doesn't work. You try an indirect and that really doesn't work, you know. And so you go back and you try a direct proof again and it's like, oh, okay, well I could do this other thing. And you go for that. How would we reference the theorem for odd n times odd? Is it just a prior proof? No, go ahead and prove it. So actually do this, right? N is odd, and work through and show that n squared is odd. Now, if on the same homework exercise we have that question, which I don't think we do, but you know, if question 3 was show that the square of an odd is odd, then for question 4, you know, you could say from question 3 we know this, and you could go from there. But for these questions, you know, you got to actually write it down as part of the homework. But this is a pretty straightforward direct proof. I think we even did it in class. We did a version of it. And so use the definition of odd, right? Write n is 2k plus 1, square it, and show that that can be put in the form of 2 times some other integer plus 1. That tells you n squared is odd. Cool. Other questions? All right, let's go on. "26 people, pretty good." Don't need that. All right, so we were talking about congruence. And things we can do with congruence of numbers. So, really quick refresher. If we say A is congruent to B modulo M, means A divided by B is some quotient with a remainder of M. In elementary school speak, B goes into A Q times with M left over. Okay, so I'll use the same kinds of examples I was using last week or last class. 17 is congruent to 2 modulo 5. Because 5 goes into 17, what, 3 times? That gives you 15, so you have a remainder of 2. So modular arithmetic is about just thinking about the remainders, throwing away the quotients, just looking at what's left over. And the basic reason for being interested in doing that is that if we have really large numbers divided by 3, the remainder is either 0, 1, or 2. The remainder is a small number. Our number could be, 10 gazillion and 15, but the remainder when we divide by 3 will just be 0, 1, or 2. And so a lot of our questions about numbers can be solved by looking at arithmetic of the remainders, and dealing with the remainders is usually easier because the remainders are just smaller numbers.
So real quick though,
yeah.
You have A equivalent to B mod M, which means A divided by B equals a quotient with the remainder of M.
Correct.
Partly of 17 is equivalent to 2 mod 5, where the remainder is 2.
Mod 3. Thank you. Actually, it is equivalent to 2 mod 5, because 17 divided by 5 is 3 with a remainder of 2. Right?
So then, wouldn't it be on the top, would it be A over M equals Q with the remainder of B?
Yes. Thank you. All right. So if you want to know, yeah, it means that A divided by your moduli gives you some quotient with the remainder of B. You're right. Thank you. All right. So, yeah, so A congruent to B mod M means if you take M and divide it by M, you get B left over. And on homework questions or test questions, if I ask you something like, 17 is congruent to what? Modulo 5. The understanding is I'm looking for a number bigger than or equal to 0 and less than 5. If we don't constrain it, I could say 17 is congruent to 17. And that's absolutely true. Right? 17 divided by 5 is 0 with 17 left over. But that's clearly not terribly interesting in most cases. Okay? So we're looking for a number in general bigger than or equal to 0 and less than the moduli. Okay, this gets interesting when we have negative numbers. So if I take negative 17 and I want to know what that's congruent to modulo 5, well, negative 17 divided by 5 is, I don't know, we might think it's negative 3. That gets us to negative 15. What's the stuff left over? It's actually a remainder of negative 2. And if we want our congruence be between 0 and 4 in this case, negative 2 is not an acceptable answer. But here's a better way. 5 goes into negative 17 negative 4 times. That gets us negative 20, which is too small. We have to add a little bit more. How much do we have to add? We have to add 3 more. So negative 17 is actually congruent to 3 modulo 5. It is congruent to negative 2 also. It's congruent to negative 17 also. Okay, so this idea that this thing should be between 0 and 5 minus 1 doesn't mean that 17 is not congruent to negative 2. It is. Okay, but there is always a unique thing that a number is congruent to, where that thing is bigger than or equal to 0 and less than the moduli. Okay, and that's often the thing that we're looking for. But nonetheless, we can use this to build up an alternate view of congruences as follows. So suppose A is congruent to, let me just call it some remainder, modulo m. Let me call it remainder 1. Okay. This tells us that A is equal to m times some integer plus a little bit left over, remainder 1. Right, where k1 is an integer. Well, suppose A is also congruent to some other value, r2 modulo m. Well, that means A can be written as m times some other integer k2 plus this other remainder r2. And we're not worrying about the requirement right now that these have to be between 0 and m minus 1. Okay, we're just thinking of this as saying that if you take a and divide it by m, you have r2 left over. All right, so a is some multiple of m plus r1. A is also some different multiple of m plus r2. Well, another way of thinking of this statement here is that if we take a and we subtract r1, that's a multiple of m. And down here, if we take a and we subtract r2, that's also a multiple of m. So saying that a is congruent to r1 modulo m is analogous to saying m divides a minus r1. And saying a is congruent to r2 is the same as saying m divides a minus r2. So here's an alternate definition. A is congruent to b modulo m if and only if m divides their difference. So two numbers are congruent modulo m if their difference is a multiple of m. All right, so we have a lot of things going on now. We have divisibility. We have remainders when we do division, And we have this notion that if two things have a difference which is a multiple of m, they're congruent to each other modulo m. In other words, they would have the same remainder when we divided by m. And we have this set of theorems and this corollary from Monday about adding and multiplying things modulo m. And so, for example, if A is congruent to R1 modulo m, and B is congruent to R2 modulo m, well, A is congruent to R1. This means m divides A minus R1. B is congruent to R2. This means m divides B minus R2. Well, the claim I'm going to make is that A plus B will be congruent to R1 plus R2 modulo m. And we can see that this is true without doing too much work. So let's prove this, and it's barely worthy of a proof. So m divides A minus R1. That's a hypothesis, which means A minus R1 equals m times some integer k1. We have m divides B minus R2. That's a hypothesis. I guess I'll list these. That's a hypothesis. That's a definition. This is a hypothesis. If m divides B minus R2, then B minus R2 equals m times some possibly different integer k2. That's a definition of divisibility. Well, let's add 2 and 4 together. A minus R1 plus B minus R2 equals m times k1 plus k2. That's good old algebra. And so let me just group my terms differently. A plus B minus R1 plus R2 equals m times k1 plus k2. That's more algebra, right? A plus B, and then I took R1 plus R2 and put a minus sign in front of it. Well, now I have two things whose difference is a multiple of m. And by definition, that means A plus B is congruent to R1 plus R2 modulo m, and that's just the definition of congruence. So there's our QED. And there's really no deep insight here. This is really just using this basic definition that if two things are congruent, then their difference is a multiple of m. Well, from that, we get if A is congruent to R1, B is congruent to R2, then A plus B is congruent to R1 plus R2. And clearly, and this would be called a corollary, A minus B will be congruent to R1 minus R2. And how do I know that? Well, do the exact same proof, but instead of adding these together, subtract them. So addition, let's see, step 6 and 7. Okay, let me do those a little more carefully. So step 6, step 6, A plus B minus R1 plus R2 equals m times K1 plus K2. Our definition of congruence, did I write it down even? Let me use different symbols here. X is congruent to Y modulo M if and only if M divides their difference. Okay, that was our definition of, our alternate definition of congruence that we did here. Alright, so now I'm just calling this X and I'm calling this Y. And I'm noting that X minus Y is a multiple of M, right? So M divides A plus B minus R1 plus R2. Right? Because this thing is M times an integer. And since M divides that minus that, this means the thing we called X is congruent to the thing we called Y modulo M. Alright, so let's make a factoid sheet. If A1 is congruent to B1 and A2 is congruent to B2, then A1 plus A2 is congruent to B1 plus B2, and A1 minus A2 is congruent to B1 minus B2. And if A1 is congruent to B1, and I'm going to stop writing modulo M, everything's going to be modulo M for the next few minutes. If A1 is congruent to B1, and we pick some integer C, well, this says A1 minus B1 equals M times some integer. And so A1 minus B1 times C is equal to M times C times K1. Right, I'm just multiplying both sides by C. And this is equal to C times A1 minus C times B1. And this is equal to M times a different integer, C times K1. Well, here I have two things whose difference is a multiple of M. And so C times A1 must be congruent to C times B1 modulo M. So we have a third factoid. C times A1 is congruent to C times B1 for any integer C. And so in particular, A1 times A2 would be B1 times B2. Well, I guess we have to show that too. I won't show that, but you can do it exactly the same way. A1 times A2 will be congruent to B1 times B2 modulo M. So do we need to write mod n instead of percent n? Yes, you do. Because percent n is an operator, right? It's like asterisk n for multiplication. Percent n says divide and give me the remainder. And this is not an operation, okay? This is stating over what moduli we're writing this statement. Right, so it's a very different thing here. So yeah, write out MODN or MODM or whatever your moduli is. Alright, so we can add, we can subtract, we can multiply by constants, we can multiply by other things, and our equality modulo M is preserved by all these operations. And that's really useful. Okay, that's going to basically let us do algebra over congruences. All right, and then somebody asked, does M divide via algebra? So division is a different story. Division is always tricky, all right? And it's interesting, you know, when you learn how to add and subtract, for most people, addition feels a little easier than subtraction, right? At least for me it did. When you learn to multiply and divide, multiplication feels a little easier than division. When you do squares and square roots, doing squares feels a lot easier than doing square roots. There seems to be a lower energy direction to these pairs of operations. And definitely when we work over modular systems like this, division gets a whole lot harder. Same thing with matrices. Multiplying matrices, yeah, it takes a lot of work, but it's a very straightforward process. Dividing matrices, you need to calculate an inverse. And an inverse will ruin your day, right? In some cases, trying to invert a matrix. It's just a lot harder. But we want to talk about division really soon. All right, but this is basically leading up to the idea that we can do arithmetic modulo m, and it somehow is related to doing arithmetic on just plain old integers. And this is the linkage that we'll use to do lots of powerful computation without having to deal with really big numbers. We'll reduce things to modulo some small number. Okay, so let's look at some examples of this, and then we'll talk about division. So examples of modular arithmetic. So let's work modulo 3. So that I don't have to think too hard right now. So 17 is congruent to 2. It's 2 more than a multiple of 3. $193 is congruent to 1. It's 1 more than a multiple of 3. All right, so let's see that. 193 divided by 3 is 64.33333. 193 minus 3 times 64 is 1. Okay, so 193 is 1 more than a multiple of 3. So I'm not lying to you here. All right. 193 plus 17. What's that going to be congruent to? It's going to be congruent to 2 plus 1. 2 plus 1 is 3, and 3 is congruent to 0. So without really doing any hard work, 193 plus 17 is guaranteed to be a multiple of 3. So 193 plus 17, that's 210. 210 is exactly 70 times 3. If I multiply these, 193 times 17, I don't know what that number is. I'd have to do some work, but I know what it's congruent to. It's congruent to 1 times 2, which is just 2. So this product is guaranteed to be 2 more than a multiple of 3. So 193 times 17 is 3,281. 3,279 divided by 3 is exactly 1,093. So this number, 3,281, 2 more than a multiple of 3. But I didn't have to use a calculator to know that, because I know this congruence is the same as 1 times 2. So here we're moving from doing work over the whole range of integers to doing our work over a very small set of integers. Because I can reduce everything mod 3 to being congruent to either 0, 1, or 2. And if I know how to add, subtract, and multiply zeros, ones, and twos, I can do all of my calculations, no matter how big these numbers are, by just doing them on 0, 1, and 2. Suppose I want to take 193 and raise it to the 13th power. Well, that's 193 raised to the 13th power. What remainder am I going to get when I divide that by 3? Well, 193 is congruent to 1. So 193 to the 13th is going to be congruent to 1 to the 13th, which is just 1. So I know this big number that I got is 1 more than a multiple of 3. So if I take this number, subtract 1, so I'll end it with a 2, and divide it by 3, it's a perfect multiple of this number, which is an integer. All right, this is powerful. This is something that we can use in computer science to do calculations on really large numbers and answer questions about them without having to deal with the large numbers. Because doing this kind of thing, this is a lot of work, right? Being able to take this number and raise it to the 13th, we can't just throw that into our floating point unit, right? Or if we wanted to raise this to, you know, the 1,345th, we got a big number, right? The hardware in our machine can't handle that as integers. We have to do this digit by digit and do, you know, basically what we do with pencil and paper. But I can guarantee that this thing is going to be congruent to 1. Be 1 more than a multiple of 3. All right, so we can do math modulo m. So I'll tell you my geeky prime number story from when I was a kid. So I learned about primes when I was pretty young, and I was fascinated by them. The idea of numbers that, you know, couldn't be divided by anything except the obvious candidates. And there was no pattern I could see to these prime numbers, 2, 3, 5, 7, 11, 13, 17. They jumped around. Sometimes they came right next to each other. Sometimes they were 8 or 10 apart. And that fascinated me, and I started playing around with them. And somewhere along the way, somebody told me the fact that nobody knew how to generate prime numbers, right? And this is still true today. Although a lot of people have tried, especially several years ago when people started mining bitcoins, the key to that turned out to be largely trying to generate big prime numbers. So I wanted to find a formula to generate primes, and I was going to tell the world about this and be rich and famous and build my dream house with a dedicated pizza kitchen next to the kitchen. So I started trying to figure out formulas that would generate primes. And mostly I came up with formulas that generated, you know, 3 or 4 or 5 primes in a row, and then made numbers that were too big for me to tell if they were prime or not. But it looks prime. I think I got it, you know. And so I was convinced I had one of these formulas, and I wrote to a mathematician at University of Illinois. His name was John Selfridge. He's since passed, but he wrote a book on number theory that I'd been reading. And I told him, you know, I have a formula, I think it generates primes and so on. And he wrote a letter back to me. I was like 12 years old, right? So I was impressed later that he actually responded to me. And he wrote me this big long letter and, you know, thanked me for my interest and all this kind of stuff. And he had a paper tape from a calculator, you know, one of these desk calculators that can basically add, subtract, multiply, divide. And in about this much tape, he showed me that the number I had sent him, which had, you know, like 15 digits, was not prime. And he did it by doing these kinds of things, right? By working modulo some thing that was a divisor. And he didn't have to do all of the complex calculations that I was trying to do and couldn't. He reduced it to a much simpler set of calculations. And that totally blew my mind, right? And so I fell in love with this idea of working in modular systems and started digging into that. And it turns out, you know, this is something that we use today. This is how we do things like, generate large hashes like SHA, or come up with public-private key pairs to authenticate over a wireless system. We need to be able to run these really big numbers, right, with like thousands of digits through these formulas, and in the end reduce them modulo something, and we can do the reduction anywhere along the way that we want. So instead of taking this number and raising it to this power and then dividing by 3, right, we can take this number divided by 3 and raise that remainder to that power and get the same answer. So that's the basic idea of why we're working in modular systems. All right, so let's talk about tables and division. So when you're in school and you're learning about arithmetic, you're learning how to multiply and divide and add and stuff like this, mainly addition and multiplication. What do? You make a big table, right? And it's usually a poster sitting on the wall of the classroom, and it looks something like this. And depending when you went to school, the numbers might be different. But let's say this is the addition table, and this goes down, and I think it went up to 12 or 15 in my classroom. It might go up to 20 for some people and so on. And what you do is this is filled in, and it shows you how to add. And so on. Right? So the good old addition table or the good old multiplication table hanging on the wall. Now this doesn't tell you how to add everything, right? Because if I want to add 234 to 11, well, I can use this and say 4 plus 1 is 5, and 3 plus 1 is 4, and 2 plus 0 is 2, right? But I have to use an algorithm. But this gives us, the ways to do single-digit addition. But, if you want to add 17, you got to do 7 plus 4 is 11, and you got to know this trick about just writing down a 1 and carrying that over and getting a 5, right? And it's fairly complicated. Well, in modular systems, all we need is the table, and the table is not infinite, right? The reason we have to learn these additional tricks in school is because we can't make a complete table for adding numbers together, unless it was infinitely large in both directions. But in modular systems, a finite table will show us everything we need to know about doing addition or subtraction or multiplication. So let's do an addition table modulo 3. So every number can be reduced to being congruent to either 0, 1, or 2 modulo 3. So all I have to do is fill in this table. Well, it's not terribly surprising. 1 plus 2 is 3, which is also congruent to 0. 2 plus 1 is 3, which is also congruent to 0. 2 plus 2 is 4, which is also congruent to 1. It's 1 more than a multiple of 3. There's your whole addition table modulo 3. All right, if I do this for multiplication, that's almost easier than doing addition. So 0 times anything will be 0. So we've got more than half our entries filled in without doing any work. And 1 times anything will just give us back that anything. And the only thing we really have to multiply is 2 times 2. 2 times 2 is 4, just like 2 plus 2, and 4 is congruent to 1. So there's a multiplication table for modulo 3 multiplication. All right, when we write multiplication tables, we're usually not going to bother listing these zeros, because they just kind of take up space. And we know that anything times 0 is going to give us a 0. So let's write a multiplication table modulo 5. And let's keep it kind of simple by not bothering to list the zeros. And let's see what we get. So this is going to be multiplication, 1, 2, 3, 4, 1, 2, 3, 4. All right, so 1 times anything is just going to give us our anything. And multiplication is commutative, right? So this is always going to be symmetric around the diagonal. So 2 times 2 is 4, that's 1. 2 times 3 is 6. And, oh, sorry, we're going mod 5. So 2 times 2 is 4. 2 times 3 is 6, which is 1 more than a multiple of 5. 2 times 4 is 8, which is 3 more than a multiple of 5. So 2 times 3 is 1, 2 times 4 is 3. 3 times 3 is 9, which is 4 more than a multiple of 5. 3 times 4 is 12, that's 2 more than 10. And 4 times 4 is 16, that's 1 more than 15. So there's our multiplication table, mod 5. All right, let me do modulo 4. All right, 1, 2, 3, 1, 2, 3. 2 times 2 is 4. 4 is an exact multiple of 4, so this is 0. 2 times 3 is 6, that's 2 more than a multiple of 4. And 3 times 3 is 9, which is 1 more than 8. So that's 1 more than a multiple of 4. All right, so here's our multiplication table. Now, just comparing these two tables kind of visually, other than the fact that this one is larger than this one, is there anything else that jumps out as being particularly different between this table and this table? Something with respect to the numbers that we find inside the table. The middle square, what about it? So 4 and 1. So we got a 4 and a 1 and a 1 and a 4 in here. What's in the middle of this one? We've got a 0. Do we find a 0 in this table at all? No. There's no zeros. In this table there is a 0 in the middle. So this has a 0. This does not have a 0. And that's actually related to another subtler fact or observation about these, which is in this table, every row and every column includes a 1. But in this table, for example, this row does not include a 1. And this column does not include a 1. And that's related to the fact that this row and column contains a 0. So someone says that's because 4 is even and 5 is odd. That's part of it, but it's actually even cooler than that. Because if I do this for the number 9, I'm going to see the same kind of thing. If I work mod 9, 3 times 3 is going to give me a 0. And so the things that will have a 0 are also mod 6, mod 8, mod 9, mod 10, mod 12, mod 14, and mod 15. And the things that won't have a 0, and every row will include a 1, will include mod 5, 7, 11, and 13. And so this has to do with prime numbers, exactly. So modulo a prime number, we will not see any zeros in this table, and every table will contain a 1. Modulo a non-prime number, there will be zeros in here, and there will be rows that don't contain a 1. And so there's this link between prime numbers and the behavior of these simple multiplication tables. And this leads us directly into division, because what is division? Division, if we want to do something like A divided by B, is really A times 1 over B. If you've done linear, that's what we learn in linear algebra. To divide two matrices, we multiply one by the inverse of the other. Well, what does it mean to say 1 over B? It means there's some x such that if we take b and multiply by x, we get 1. Well, if there's a 1 in this row, it means that 2 has an inverse. There's something we can multiply 2 by to get 1, in particular 3. If there's no 1 in this row, there's nothing we can multiply 2 by that will give us a 1. 2 does not have an inverse. All right, grand punchline, modulo a prime number, every integer other than 0 has an inverse, which means we can do division if we're working in a prime moduli. If we're working in a moduli that's not prime, some numbers do not have inverses. That's going to come back in glorious fashion when we do RSA, because we're going to need to find inverses, and this is one reason we're going to use prime numbers to do our public key crypto systems. And primes pop up everywhere. They pop up in nature. They pop up in the emergence of locusts every 13 or 17 years. They pop up in all sorts of unexpected places. All right, so that's the end of our time for today. So keep working on homework 4. Bring questions on Friday. We'll dig deeper into here. We can talk about locusts on Friday. And have a good afternoon. I will see you next time.